Welcome to This Explainer. You know, we hear constantly about AI getting smarter. It's rating code, it's passing bar exams, it's drafting incredibly polite emails in a matter of seconds. But behind the scenes, there is a massive, totally hidden architectural shift happening right now that rarely makes the mainstream headlines. Today, we're going to unpack how AI is transitioning from being this fragile, sometimes unpredictable parlor trick to becoming structured, safe, and durable enough to actually run the real world. We're looking past the hype of massive language models and diving deep into the invisible infrastructure that finally makes these systems reliable for our everyday, high-stakes operations.
So think about this paradox for a second. Why is it that the exact same AI that can brilliantly write a 5-paragraph essay in the blink of an eye will confidently produce absolute, complete garbage if you ask it to run a multi-day research project? I mean, when tasked with something complex, it might hallucinate an entirely fake market research report or try to book a flight to the wrong continent. Resolving this paradox, bridging that massive gap between a quick trick and a sustained, reliable job, is absolutely the key to unlocking the next era of automation.
Here's how we're going to break this all down today. We'll start by examining the core memory problem holding these systems back. Then we'll look at the absolute chaos of scaling multiple agents to work together. From there, we'll dive into the specific engineering solutions used to actually govern them. And finally, we'll bring it right back to exactly why this deeply technical infrastructure matters so much to you and your everyday digital life. Let's get right into it. Well, the root of the whole issue is something called the agent memory wall. And the crucial point to understand here is that this isn't just some random bug in a specific model from OpenAI or Google. It's a fundamental structural problem where an agent simply runs out of working memory or tokens as a job drags on. Think of a token roughly as a single word or syllable. It's literally just like a human trying to hold 50 different phone numbers in their head while simultaneously trying to solve a complex math problem. Eventually, things just start slipping away, and the system loses the plot entirely.
Because of this memory wall, long-running agents fail in highly predictable ways. And actually, just throwing larger and larger context windows at the problem doesn't fix a thing. Even if a model can theoretically ingest 1 million tokens, its attention naturally degrades, the computing costs absolutely skyrocket, and the errors just endlessly compound. Take evaluation blindness, for example. A tiny, almost unnoticeable error in step 2 of a massive task endlessly snowballs by step 50, creating what developers call confident garbage. The AI has completely derailed, but it's continuing to execute tasks with absolute, terrifying certainty. Oh, and if the server suddenly restarts mid-thought, boom, the entire history is lost.
And this brings us to the ultimate dividing line in modern AI. It's the critical difference between a task and a job. A proof of concept works perfectly on isolated tasks, right? Like translating a single paragraph or summarizing an article. But real, everyday enterprise workflows require long-running jobs. Jobs accumulate state, meaning the AI has to actually remember what happened yesterday to make an informed decision today. They branch conditionally based on brand new information, and they span across multiple sessions and days. You simply cannot solve a real job in a single one-off prompt and response cycle. I love this analogy from the folks over at MindStudio because it perfectly captures this necessary shift in how we build things. They noted that while everyone else built a construction worker, they needed to build the contractor. Think about it. Instead of having one highly stressed out worker furiously trying to remember every single detail of a massive building blueprint while simultaneously hammering nails and pouring concrete, you need a manager. You need an orchestrator, coordinating external memory, tracking the overall progress, and delegating specific, bounded tasks to specialized subagents. Now, when we look at the MAST framework, we discover exactly how these multi-agent systems actually break down in practice. And it's fascinating because the failures aren't just about writing bad code. Get this, over 40% of failures stem from system design issues, like agents getting stuck in endless, looping cycles of step repetition. Even more surprising, over 32% come from deep inter-agent misalignments. Turns out, AI agents can be just as bad at office politics and communication as we are. They frequently ignore each other's inputs, misunderstand basic instructions, or outright hoard critical information instead of sharing it with the team. So when you just throw multiple agents together into a system without strict supervision, you're essentially inviting complete chaos. Research shows that race conditions increase quadratically with the number of agents. In some real-world customer service workflows, just passing messages back and forth between different agents takes 950 milliseconds, while the actual thinking, the raw AI processing, only takes 500 milliseconds. Think about the absurdity of that for a second. The coordination overhead literally outpaces the actual work being done. It's incredibly inefficient.
And all of this chaos brings us to a harsh, unavoidable realization. Unchecked AI capabilities create massive, uncontrolled blast radiuses in the real world. Think of a blast radius as the amount of damage a system can do if it goes completely off the rails. If your AI is now empowered to execute live code, interact with your angry customers, or spend company money, you absolutely cannot afford a silent failure or a hallucinated command. Governance and strict guardrails have to be firmly installed before you ever unleash the model. To solve this exact problem, developers are borrowing a brilliant concept straight from cloud networking and systems like Kubernetes. The industry finally realized we have to separate the data plane, which is the cognitive engine that's actually reading text and doing the complex reasoning work, from the control plane, the steering wheel that manages how the entire system operates. The control plane doesn't think, it simply governs the thinkers. It ensures the agents stay in their lanes and follow the rules, no matter what. In action, this control plane provides absolutely critical safety nets. For example, if a provider like OpenAI unexpectedly goes down, the system doesn't just crash. It seamlessly, with literally zero delay, routes over to a backup model like Anthropic. It strictly whitelists specific tools, actively shaping requests so the AI can never feed broken, hallucinated parameters into your database. It acts as a giant circuit breaker, detecting failures and auto-recovering on the fly. This architecture is the definitive boundary between a fragile tech demo and a robust, production-ready product. By layering an orchestration engine like Temporal's durable execution right over an agent framework like LangGraph, developers get the ultimate safety net. Imagine an AI is processing a complex, multi-day insurance claim. It's verifying documents, checking policies, the whole shebang. If the server suddenly crashes halfway through, Temporal makes sure that the AI picks up the exact next step when power returns, without losing an ounce of its memory. Meanwhile, LangGraph is safely handling all the actual reasoning and tool execution behind the scenes. And this level of absolute control is vital, because when we move into high-stakes systems of record, like SAP, for instance, actions are entirely irreversible. If an AI is allowed to just release a massive purchase order or alter critical financial data, there's no simple undo button to click. In these high-stakes enterprise environments, an unmonitored, fully autonomous agent isn't an impressive technological leap. Actually, scratch that. It's more like a massive corporate liability just waiting to happen. Which is exactly why keeping humans in the loop isn't some sort of limitation. It's the defining architectural feature that makes these workflows trustworthy in the first place. Before executing a major, irreversible action, the workflow is hard-coded to automatically pause. It assesses the risk, sends an approval request via a messaging app like Slack or Teams, and literally just waits. A human expert reviews the audit trail, clicks approve, and only then does the workflow safely resume. It perfectly marries blistering AI speed with careful human judgment. So what does this all mean for you, the everyday person? Well, all of this invisible, deeply technical infrastructure basically boils down to one word: trust. It means the AI handling your customer support ticket isn't going to just drop your case if a server restarts somewhere. It means strict tool governance actively prevents a rogue AI from accidentally leaking or corrupting your personal data. But most importantly, it guarantees that when AI interacts with your finances or your highly sensitive health records, a real human being is always mandatorily holding the keys. You get the benefits of AI without the scary blast radius. Thank you so much for joining me for this explainer. As we finally transition away from chaotic multi-agent experiments and move toward these highly durable, governed control planes, the real-world possibilities are just staggering. We are finally bringing true, reliable order to the wild chaos of artificial intelligence, making it safe enough for the systems that run our daily lives. So I'll leave you with this thought. Knowing the guardrails are finally securely in place, what complex, unbounded job will you trust AI to tackle next?